Okay, so this is lecture number 5, and do you have any questions from the previous class? Anything? Okay, so I will post the notes because do not have the recorded lecture right now. So today we have seen like the frequency acquisition in type 1 PLL and type 2 PLL, and both these frequency acquisition we see in context with the sinusoidal phase error detector. Now there exist many other phase error detector, and since this is the first clock which detects the phase error between the input and the output clock, we will look in different kinds of phase error detectors today. So this is phase error detector, and just like quantify them in terms of their gain and other things. Okay, so there are two kinds of phase error detectors which exist. One is analog, and this is something which you have seen before as a multiplier, and other is digital. And within analog there are the one which you have seen is multiplier. Okay, then there is another is sample and hold. We will see what are the pros and cons of each and where we can use either of them. Then in terms of digital, you have exclusive XOR phase detector, you have SR flip-flop based phase detector, then you have the two state. Oh, this one is so you have three state phase frequency detector normally, which is called, and you have D flip flop based phase detector. Okay, so we will see if there exists any more which we normally use. We'll go one by one. So first one is multiplier based phase error detector, and I would say this we have seen all. So you have the input signal is still a voltage in terms of the actual signal which is being used. V out is the output of the PLL, and this multiplier output is V error, or let me just say this is VPD, phase error detector output. Okay. Now here signal V in is an analog signal, A in sine of omega t, and V out is also analog signal, A out sine of omega t minus delta phi. Let me just say delta phi is the phase difference between the two. So the output of the multiplier is V in V out, which is, I will just write it directly here, A in A out by 2 into cosine of 2 omega t minus delta phi minus cosine of delta phi. Okay, I just applied the trigonometric identity directly here. Now the average of the multiplier phase error detector, when you take over time or you filter it in the other sense, you will have A in A out by 2 cosine of delta phi. Okay. Now the if I plot the transfer function, no, plot the input versus output characteristics of this phase error detector, if delta phi is, so let me just say I am writing phase error as A in A out by 2 into cosine of phi error. Let's just call it that phi error. So I'm just using this as phi error is equals to delta phi. Okay. Now, so this one will be something non-linear which you have seen, and This is a little bit hard. So VPD average phi error says minus pi by 2 plus pi by 2 pi and minus pi. Okay, and this amplitude is dependent on your A in and A out. Okay, so now in this particular phase error detector, we have seen as per the stable locking reason, if the two frequencies are the same, is this one. Okay, so that you can say I'm using the same stability locking condition which I have shown you during the null thing, right? That there were two nulls and at which null does it settle. So if you use the phase error with respect to the whole PLR equation, you will find that. Okay, so now this is just a phase error input output characteristics, and can you just say at which, okay, possibly at which of these, if the two frequencies are the same, where will it lock to? If this is a phase lock loop, if the two frequencies are the same, it should lock to a zero phase error. Okay, and you are seeing there are two zero phase error points. One is minus pi by 2 and the other is plus pi by 2. So which one will it lock to? Pardon? Minus pi by 2. This is as per the stable thing that you keep. If any delta changes happen, you again come back to the null. Okay, so I will just make a transition on the x-axis and say phi e s is equals to phi e plus pi by 2. Okay, so this will be, I will now I plot the with, pardon? No, see sign of the feedback. If you are saying pi by 2, then you should see. So let me just tell you this. If you are saying something, if I change the sign of the feedback, means positive becomes negative, or this kind of thing you are talking about, right? So that is changing the sign of the feedback here. How will it translate to? So right now what we are saying is here the delta phi should be equals to minus pi by 2, right? So in the other condition you will just mean if this is the case, yes, that will happen. So here the, let me just see, yeah, if you are changing the sign of the feedback, changing the sign of the feedback will reflect in the delta phi which you are considering. Okay, so no, this is just to show you that. So it will become more clear when I will translate this phi e to phi es, that you will see a linear, slightly a linear slope at PES equals to 0, which is nothing but just a mathematical way of representing it. Okay, there is nothing, means I can do all the analysis at this point itself. There is nothing which is stopping me to do it. This is just another way to say that okay, I lock to a zero steady state phase error. Okay, so if I just shift it by, okay, this is no more a sinusoidal, but man, minus pi by 2 and pi by 2. It's just a translation. Okay, so the things which you note here is that this phase error detector is monotonous in range phi E S, that range is monotonous range. Let me just write it as for phi S is plus minus pi by 2. If you are anywhere other than plus minus pi by 2 of this range, you are not yet proportional to the phase error. Okay, so this is this. Okay, the important part is this is not a linear range. This is still a non-linear curve, but the only thing is this is monotonous in the sense. Okay. Now, when you are using this phase error detector in a PLL loop, you are considering all the small signal analysis. So you need to know that in the locked state, what is the gain of what is the loop dynamics of the PLL, for which you need to know what is the gain of the phase error detector. Okay. So the gain of this phase error detector is defined as KPD, which is, this is also defined on the average of the phase error detector output with respect to the phase error. So this is equal to minus A in A out by 2 into sine of phi. Okay. Now I'm just applying on this this equation, right? So for that, let me just remove this. If I plot the gain curve here, this is actually the sine of phi. This one is there any? Okay. Is there any minus sign missing somewhere? No. Okay. So you have sine of phi is this. This is the gain curve. Is it? So is there anything wrong here? Pardon? Before the shift. I'm plotting it before the shift because this differentiation is here only. Okay. So you can treat this gain as a very like a constant gain over a very small range at the locking point, minus pi by 2. Okay, but the gain is still, if you are away from the minus pi by 2 locking point, your gain is still nonlinear. So this particular phase error detector, if I summarize it, it has a nonlinear gain at locking point, at locking phase error phi e equals to minus pi by 2. Okay, and nonlinear gain leads to nonlinear loop dynamics. So you cannot easily say that, okay, I will use this gain and all my bandwidth and everything will follow if you are having more phase error in the system. Okay, and the second thing is that the range of this phase error detector, monotonous range of this phase error detector is limited, which is minus pi by 2 to plus pi by 2. That I am writing with respect to phi is S. So within this range, you can approximate some kind of loop dynamics for this phase error detector, but you still need to be cautious about that what is the offset or other thing. So let me just say that for an example, right, if you're using a PLL initially with some particular phase error, right? Then you will lock to a certain phase error offset on an average value. That means your locking point will not be any more pi minus pi by 2. Okay, your locking point will be somewhere here, let's say this point. So then your the phase error detector gain which you are using for the loop, the stability of the loop is different. Okay, yeah. Mm. No, so the thing is, now if you say there is, so what's the condition whether you are in a phase error of, whether first thing is whether there is a frequency error or not, right? So this is again coming back to the same thing where I have told that let's say you start with this point. Good question. Let's say you are here, right? Where the gain of the loop is 0. Okay, so which way will it go? Means it may go slowly to one condition, but that is not the stable condition. So the gain is lesser, but the system is not stable. So you will track this path. Even if let's say you are means this is one point which I have seen. Let's say you are at this node, something here. Okay, so you may either go to this or come to this depending on how much delta shift you have. So yes, you are right. You may start the loop where you are having the loop gain, or the gain of the loop is very minimal. Okay, but the stability means the stability of the whole loop will force you to come at the zero locking point, provided there is no frequency error here. Okay. Any questions? So this is one of the analog phase detectors, which is I would say not that much used these days because realizing a good multiplier is not that easy. It's more power consuming in the circuit, and you also see that this is actually dependent on the input amplitudes. Okay, so the next one is sample and hold phase error detector. Okay, now let me show you a very simple. How can you detect with a sample and hold circuit? Okay, so let's say, okay, assume that these are sine waves, though they are not. So okay, something kind of this. So let me just make it that this is t, 2t, 3t, and something, and this is t by 2. I'm just making it so that I correct myself on the plot part. 5t by 2 and other. Okay, so let's say this is the input sine wave V in. This is my V in, right? And I have a similar I have a V out which is also periodic, and I am only saying that right now assume that they are the same frequency because we are still talking of phase error detection. We are not talking of frequency error detection right now. So the thing is, if that is also a sine wave, that might be shifted from this sine wave with a phase error whatever it has. So let me just say if something V out is this way. Okay, so what you can say for sure is that this delta is going to be the same for the two shift. That is the phase error, right? So what can be done is if I sample the input with respect to V out rising as. Now I have drawn here a sinusoidal V out, but V out is also can be a square wave. because I am saying that I am going to sample it, the switch should get on or some at some point. So I am sample at all the rising edges of V out. Okay. So if I sample at all the rising edge of the V out, then these all the red marking which I have shown, they should be the same value. There's no doubt in that as such. And if the frequency is different, then you will start sampling a different value. Okay. Because every rising edge you will then sample a different value as such. So, pardon? Yeah. So first thing is we are talking here as a very deterministic system, right? So let you consider a couple of cases. The first case is, let's say, let me just write it as first case as the phase error phi e is constant. Okay. Then what you sample is always a constant value. The second case is the phase error is constant plus you have a random noise Vn, which has a mean 0. So you will keep shuffling between some value, but it's still the mean value will still remain the phi. The next case, you can say that I am having a frequency error. Okay, with no noise. Then the phase error will keep on changing in a deterministic fashion. So right now, the case which we are considering is only this, I would say. Okay, so here this is easily implemented. Let's say you sample this. Here you are having V in, and this one is V out. For your easier thinking, you can say V out is a square wave. That is, I am sampling at the every rising edge of the V out. And this is just as some block as an amplifier, and the output is VPD. Okay. So why this is better than a multiplier base? You will just look at it, because the characteristics will turn out to be the similar as your multiplier based. Okay. So if my signal V in is equals to A in sine of omega t, and I am sampling with V out, which is having a sum. So sampling it as V out will give you A in sine of omega n times t out plus delta t, right? T out is the time period of the sampling clock waveform. Delta t is the shift from time to instant t equals to 0. Now, if I consider that my T out is the same frequency as my omega, as my input frequency, then this is nothing but T is 2 pi by omega plus delta T, which I can write it as sine of 2n pi plus omega delta T, which is nothing but sine of omega delta T, or the sign of the phase error. Yeah, so what I would say is you consider that whenever the rising edge comes, you sample it. Yeah, means it is not tracking right now, or even if it is tracking, you are only considering the sampled value. Okay. So in terms of characteristics, if you look, the characteristics of this phase error detector is the same as the multiplier based phase error detector. I hope I do not need to draw the range and all those things here. So if I just say the range of this phase error detector will also be equals to plus minus pi by 2. This is the monotonous range, right? Did you get that thing, right? And the gain of this phase error detector is equals to A in cosine of phi error. The gain is also nonlinear. It changes for what phase error do you settle to. Okay. So this phase error detector also has a nonlinear gain, and then you can say, or nonlinear gain, and hence let me say loop dynamics, and range is limited. Okay, so there is another thing you see, that let's say the input frequency is omega, right? And I am sampling, if the two frequencies are the same and I am sampling at the same frequency. So what can you tell about the output, the spectrum of VPD? Pardon? It's an alias spectrum. So that thing will happen here. Okay. So VPD, now how is this going to affect? You need to see with respect to all the filtering in the loop. So VPD, which has aliased frequency spectrum. I'm not going to detail of this because it very much depends on what is the frequency difference. If you are looking at a frequency difference at which, so let's say if the sampling frequency is twice the input frequency to some, then you may not have the alias spectrum. But in phase locking case, when you are having the same frequency, it will be an alias spectrum. Okay. So if it has all this, what can you just say? What is the good thing about this phase error detector? And I can say that this is used a lot these days to have a very energy efficient failure. Means you have a separate loop to bring the frequency within the range or very close, and then you just, for the phase error correction, you just use this. Pardon? Yeah, V out just controls the switch, and this is like, you can say there I was using a multiplier, where you will have a current sources if you are using a CML based multiplier, which is more complex, right? Here this is simple, means if my clock waveform is a square, I just need to sample it. So this is one of the very simple phase error detectors and quite energy efficient in many cases. And in case of regular PLS, what happens is that your output frequency is some multiplied times of the input frequency. Okay. So when you are sampling the output frequency, you sample once in a while. So because the reference frequency is, let's say, the output frequency, just I will give you an example. Let's say F out is equals to something as 8 gigahertz. Okay. And F ref, the reference frequency, is something just like 1 gigahertz. So you still not sample at, means this is heavily alias spectrum now. If I used fref for sampling the output. So you can do two ways. Either you sample fref by f out, okay, or you sample f out by fref. If there is any phase error, you will detect any DC phase error, you will detect that. Now the thing is, if you sample fref by f out, your sampling frequency is higher. No, no, no. Yeah, yeah. So the thing is, when you get V out by N, you put a divider in the loop. No, so that is what I am saying. You can have a separate loop to bring the frequency. Okay, go this way. You have a, so I will give an example here. So let's just, so let's say we take the same case, F out and F ref, right? So let's say F free running is something as 7 gigahertz, just for example. Multiplier ratio is N equals to 8. Reference frequency is 1 gigahertz. Okay. What do you do first? You basically bring F out using the all of your regular PLL loop, bring to, this is 8 gigahertz. Okay. Then you disable divider path. Okay. And then you sample the output at the reference. Sample F out with reference. So all the thing which is happening in the divider, that is gone, your energy is reduced. We will go in this kind of PLLs in detail. So the thing is, you can say the PLL has been there since 1950s or 60s, right? And everyone wants to have a PLL with the highest frequency, lowest power, lowest jitter. So all the tried things to reduce, wherever you can reduce power consumption, you just reduce it. Okay. Yeah. Pardon? Yeah. 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 No. So okay. So the other thing is, you can say this phase error. Which what is phase error as such? If I ask you, whether it is means phase error is a way of representing the clocking the edge or sorry the clocking instant difference between the reference and the output, right? That is what we are concerned about, that the output should always at a fixed instant it should be rising edge or falling edge, right? So if you are looking in terms of phase, so okay, this is another good one which I will show you. So let us say okay, so as an example, okay, so let's say this is your f in or f ref, okay, and your f out is, so let me just, I am plotting f out as twice of f in, okay, this is f out. Now independent, and let's say this is the time difference delta t. Now this delta t, if the way you are saying that this if I look at the phase accumulation of f out, that is surely twice the phase accumulation of f in, right? That is why we basically divide the output clock by 2, and we refer everything it to the back, everything it to one single frequency. You cannot compare phi out phase which is accumulated at a different frequency directly with the phase which is accumulated at the reference frequency. You got that idea? Means phase is a dimensionless quantity. Where as soon as I say there is something called as a phase, that means it has a reference. You got, so the thing is, the reference frequency accumulates a 2 pi phase error within this period. Absolute time instant is this, whereas the output clock accumulates a 2 pi phase error within this period, right? That is why we divide it, so that we come to the same reference. But if I ask another question, that whether you divide or not, if I give you f in and f out like this, and the frequencies remain the same, there is no noise in the system, if you always look at delta t separation between the rising edge of the reference and the nearest rising edge of this thing, does it change? It doesn't. So there are two kind of analysis which happens for PLL. One is all time domain analysis, where you do not consider phase, you always go with an absolute delta t. So okay, interestingly, so let me just show this part also. Let's say I divide this clock by 2, right? So if I divide this clock by 2 and the divider has no delay ideally, so this will be, I'm just, so you see, did the delta t changed between the divided clock and the reference clock? No. So you see, when we have the, so you have your f out and a divide by 2 here, right? And this is the divided clock, so whatever phi out was here, that becomes phi out by 2, right? But the timing instant delta t does not change, that is still remain intact. So we can do all the analysis in time domain, but it's conventionally done with a phase domain analysis. Okay. So any questions on, yeah. No, can you just repeat again the question?
By this solution, can we just say that instead of implementing type 2 PLL, we have implemented type 1 PLL, which corrects the frequency error?
Frequency or phase error? Type 1 PLL cannot correct for frequency error. Type 1 PLL cannot correct for frequency error beyond a certain limit.
There will be finite
Phase offset, they will be there. Yeah. No, means, so the thing is there will only be one phase error detector. Okay, so let me say, repeat your question. What you are saying is that in place of using a type 2 PLL, I use a type 1 PLL, right? Within the type 1 PLL, which phase error detector are you going to use? This one, or are you saying that you are going to use two different phase error detectors, or only this one? Okay, so let's say you use a two different phase error detector, which I think may not be the required, because you see that this phase error detector characteristics, input output characteristics are the same as the multiplier. Right? So let's say you use a phase error detector to correct for the frequency within a certain range, right? And then you use another phase error detector like this sample and phase error detector to lock to the phase, right? So okay, let me see. I am not. So what you are saying is, let's say I use two phase error detectors. Okay, the reference to the two are the same, right? And the outputs to the two are the same. Okay, now I add it up somehow in this manner, and then I have a filter which is telling me this is a type 1 PLL, and this is a VCO, and this is what how we are closing the loop. Do you mean to say this? Okay. So first thing is, if you are using this the same kind of phase error detector, whether it's a multiplier or this subsample one, their characteristics are the same, right? So whatever V error you are getting here or V error you are getting here, that will be the same. You will not be able to distinguish between the two. It will be just some offset from one or the other. Because you see that the input output characteristics are same sinusoidal. So I can just say, I can write this is as A in sine phi E and the other part as A in A out cos phi E, right? That is the combined thing. So it will lock to some value where the phase error, the total combined phase error gives me whatever the frequency error I want. So the thing is, you have a separate loop. You have a separate phase, you will have a separate frequency detector or a phase frequency detector or a separate loop, which will bring the frequency close to a very small, like maybe at 50 ppm or 100 ppm range. And then you let this loop operate. Even in that case, you will have some way to check whether my frequency of the oscillator drifts or not. Because this phase error detection, sample or phase error detection will not work if the frequency drifts beyond a certain point. So there will be some kind of periodic check, some kind of compensation which brings the frequency back over a period of time. So that will be there. Okay. The only thing is that this is a very so let me just say, if you are operating any kind of high frequency PLL, let's say you are operating at maybe a 5 gigahertz or 10 gigahertz kind of PLL, and this will become clear that normally you want a higher reference frequency. to suppress the VCO phase noise. And operating all this multiplier or basically phase frequency detector at a high frequency will start consuming a lot of power. Whereas this sample and hold circuit is like a simple one single switch. Now here also it will depend what kind of amplifier am I using in between. What linearity does it have? So in means at least from an energy point of view, what I see is these days that is sample and hold phase error detectors, they are quite good from energy point of view. They will surely have a drawback. Means this can't do the same even if the frequency drift. If the frequency drift, you need to have a separate loop to correct for that. Okay, so both of these are analog phase detectors. The so is the question answered now? Or, okay, yeah. So that will basically become clear when we start looking at the loop bandwidth. Okay, so aliasing will surely be there. So right now means it becomes really. So I am considering only one single frequency, right? And I am sampling at another frequency. So that aliasing will be very clear because this will turn out to be a DC, right? But when you have a noise on the reference, then how does it alias? And then again, it depends on the filter bandwidth. So this aliasing with this kind of PLL, we will come back to this when we look at the whole PLL architecture and then see how this is a problem. The other thing is the reference noise is normally very low in the system, but if you alias a lot, it will be a trouble. Okay. So the next one is now we have just seen the analog phase detector. The next one is exclusive XOR phase detector. Okay, and this is digital in implementation. The way it is, uh, you have an XOR gate, and one signal is your reference, other signal is your clock. So I'm just writing as R and V. This is a terminology we use quite often here. And so let me just, and we again I am assuming that I am frequency locked with the signals R and V. Okay, so this is my R, and let's say this is certain V. So if it is frequency locked, so this is R, this is V, and this one is VPD. So VPD is something like this. Okay, this is V times PD. And just let me just say I am treating this as voltage plus V and the bottom one as voltage as minus V. Means you can treat anything 0 or 1, that doesn't make any difference. Okay, so now the average of the phase error detector out for this kind of phase error detector output is equals to V times VE phase error minus pi PE into 1 by pi. So what I have is V 2V by pi, sorry, 2V by pi into PE minus pi by 2. Did everyone get this thing right? Because uh, this is phase error pi e, and you see this is basically a periodic with pi, the phase error. So I didn't go for 2 pi, I just put it pi. Okay. Now Interestingly, this is a digital block, but it gives you a linear phase error detector characteristics. Okay, at 0 it is minus pi by 2, at other place at pi by 2 it is 0, and at pi it is v. So this is v, this one is minus v, and let's me just plot the other one. Okay, so at this is right now, so basically phi e equals to 0. I have minus phi equals to pi by 2, so this is there, phi equals to minus pi by 2. Is there anything wrong here? This one is pi by 2. So at phi e equals to minus pi by 2 minus pi. So we have to shift it and then see. Okay, so that is fine. Let me just plot it. So just a minute. So let me just work with this thing out. So you see that the gain of this phase error detector is linear in the range minus 0 to pi. As such, I can shift it and always say minus pi by 2 to pi by 2. And what is the gain of the phase error detector? KPD is D times average of VPD by D phase error, which is 2 by 2V by pi. Right? So let me just show you another case here where the phase error is greater than pi. What happens if the phase error is greater than pi? So let me just plot that part. So because these things will repeat as such. So this is R and V, and if phase error is greater than pi, so let me just bring like this. Okay, so this is V, and your XOR phase error detector will have okay. So for this, you will be again mostly positive here. So this will turn out something kind of. I'm just extending it. Okay, I think this can be redrawn. Okay. This is VPD. Is this clear to everyone? I mean, just an XORing of the signal. There's nothing. Pardon? I didn't get that. Area of the pipe? No, I didn't. I didn't get that. What do you mean? Oh, why is it the average? Okay, let me just say. Then let me look at your question. So this C is the phase error. For phi time VPD is high. That is this part, and you see that this is periodic with respect to pi. So for pi minus phi e, it is negative, which is this term, right? And I'm averaging over pi. Okay. So this is the means I'm doing it everything with respect to phase and radians. You can do it with respect to time and other. There is. Yeah, if maximum voltage is Z, that's why I tell I am. So you see there, right? That I told her that I am considering plus V and minus V here. If you are considering V and 0, then that's the other case. Means you will just have a DC shift here as such. Okay. And so if you look at when you are having a phase error of pi by 2 in this case. So let me. So what we have considered here is only pi. So let me just give another example where the phase error is pi by 2. Sorry. If phase error is pi by 2, then I will plot on top of this, that will become a little bit more. Phase error is pi by 2 means my V signal is something kind of this, right? That is a phase error pi by 2. So if this is pi by 2, what will be my output? My output will be something kind of this, right? Whose average is 0. So at pi by 2, the average of the phase error detector is 0. So since I told you this, let me just say, if this is my reference frequency or 1 by f ref, this is my reference frequency and this is my VPD, okay? In the output spectrum of VPD, where do you think the harmonics will be? Twice of f ref, right? So I will have 2 f ref and then the harmonics of that. Okay. Now this 2 f ref harmonics should be beyond the loop bandwidth. Otherwise you will see disperse with respect to this. There will be another kind of phase error detector where the harmonics are inside. Okay. So interestingly, this is a digital which is supposedly a non-linear block, and this gives you a linear characteristics. And this is also used at different places. But again, all these phase error detectors cannot correct for a frequency beyond a certain range. So one has to look for that. So just summarize this part. The range is minus pi by 2 to pi by 2. I'm just writing it after a shifted 1. And it's a linear gain. It has this particular PD. Okay. Yeah. Yeah, the thing is for that we have to go to the next class. So the thing is all these phase detectors we will see that they are able to detect the phase error, but when it comes to the frequency error they can't. So that's why there is something called as phase frequency detector. This will not be, yeah, right. Yeah, but it is a limited. So let me just say this. If you have a frequency here, let me just stop here and I will come to your thing. So